Good afternoon, distinguished guests and researchers. It's an honor to present our latest research in ICRA2024, and I'm excited to present our work on relative localization estimation for multiple robots via the rotating ultra-wideband tag. Today's agenda will cover the background of ultra-wideband UWB localization technology, the challenges we're tackling, our proposed method, and its analysis. We'll conclude with the simulation and experimental results demonstrating our system's effectiveness. Let's get started. On our background slide, we address the conventional use of ultra-wideband, or UWB, systems for robot localization. Traditionally, UWB localization with anchors has been the norm, requiring a fixed setup and initial calibration. This constrains localization to a predefined area. When using multiple UWB tags, there's no need for external anchors, but it increases costs and complexity since each robot requires several tags. And now, let's consider using a single UWB tag. This method is more affordable and suitable for compact robots. It relies solely on onboard sensors without the need for external anchors. However, it presents its own set of challenges, such as the need for relative motion between robots, which complicates fixed formations. Our response? To develop an onboard relative localization technique that requires just one UWB tag per robot. Our goal is to provide consistent two-dimensional relative localization that's independent of the robot's motion patterns. In confronting the challenges, we recognize that a single UWB tag per robot only provides one distance measurement, which isn't enough for accurate relative location estimation. Additionally, our system must seamlessly scale from a duo of robots to a complex swarm, ensuring consistent location estimation across varying scales. Lastly, we are adopting a distributed localization approach. Each robot independently computes its location using onboard capabilities, rather than relying on a centralized processor. This method enhances robustness and makes the system suitable for compact robots with limited individual computational resources. Moving on to our method, we present our innovative rotating tag design. DUD1. Might wonder about the need for a rotating tag. The core reason is that single distance measurements is not enough for localization. By introducing rotation, we ensure that the persistency of excitation condition for our relative location estimator is consistently met. This enables a precise estimation of relative locations between robots. An interesting aspect to note is the rod's length, the one holding the UWB tag. We had to strike a balance, ensuring it doesn't occupy too much ground space while still optimizing location performance. The length of the rod holding the rotating tag is adjustable. A longer rod provides enhanced localization accuracy. However, it also occupies more space. Users need to find an optimal balance tailored to their specific requirements. Delving into the design specifics of the rotating tag, the integration of a slip ring allows the tag to maintain uninterrupted rotation in a single direction. The Vicon markers employed to derive ground truth in a Vicon setting but doesn't influence the actual localization process. The DC motor's feedback on the angle is crucial for determining the tag's offset. Instead of looking at a swarm of robots as one entity, we broke it down. We divided the multi-robot system into clusters. Now, each of these clusters has a leader robot. This leader plays a pivotal role in our localization process. You might wonder, what's different about these leader robots? They come equipped with rotating UWB tags. In contrast, the followers, or the regular robots, have fixed tags. This division aids us significantly in estimating locations, both between the leader robots and their respective followers. From this division, the robot localization problem is further categorized into two types. The first involves the localization between two cluster leader robots, essentially between two rotating tags. The second focuses on the localization within a cluster, between the leader robot and the follower robots, or between a rotating tag and a fixed tag. Building on our system decomposition, we delve deeper into the specifics of location estimation. The blue dots in the diagram represent the positions of one tag at two distinct moments, while the red dots depict another tag's positions at those same moments. By vector translation, we arrive at the triangle shown in the top left corner, which yields a key geometric relationship. This geometric relationship, crucial to our methodology, holds true whether we're dealing with two rotating tags or one rotating and one static tag. Building upon this geometric insight, we designed two relative location estimators. These operate under a recursive least squares framework. Their inputs are quite similar. Tag offset, obtained from the brushless motor, distance sourced from the UWB tag, and velocity, derived from the odometer. The leader can broadcast the estimated relative locations between leaders to all follower robots in its cluster. This allows us to determine the relative location between any two robots, as indicated by the bottom formula. In our convergence analysis, we've rigorously demonstrated that the proposed relative estimation algorithm converges to the true values at an exponential rate under ideal conditions. Our simulations demonstrated that the length of the rod has a substantial impact on our algorithm's efficacy. For rods of 0.5 meters, 0.35 meters, and 0.2 meters, the estimation error in the x and y dimensions converges to 0, showing that height variations along the z-axis do not influence the outcomes. Importantly, a longer rod, especially the one measuring 0.5 meters, significantly accelerates the convergence rate. In our simulations focused on the forgetting factor's impact, we noted an initial large error, so we highlight results starting from 0.5 seconds onwards. Between 0.5 and 1 second, a larger forgetting factor led to bigger errors. However, from 1 to 5 seconds, A forgetting factor of 0.99 resulted in the smallest error, and from 5 to 20 seconds, a larger forgetting factor consistently minimized the error. This pattern indicates that an increasing forgetting factor initially slows the convergence rate, but ultimately enhances localization accuracy and reduces error variance. The outcome suggests improved resistance to noise with a higher forgetting factor. In analyzing the effects of noise on our localization system, we observed the root mean square, RMS, and standard deviation, SD, of errors across dimensions. The data, summarized in the table, show a clear trend. As noise levels rise, both the mean and variance of the estimation error increase. However, it's crucial to note that the level of error remains significantly lower than the actual noise level, highlighting the robustness of our algorithm against environmental noise. In our first comparison experiment, we tested our algorithm with a rotating tag rod length of 0.1 meters and a rotation speed of 120 revolutions per minute. For contrast, we used a multi-tag setup with 4 tags on a 8.1 meter radius circle, and we also applied the extended Kalman filter, EKF, to the rotating tags data. Throughout, robots were stationary to maintain uniform test conditions. The results, as summarized in the table, demonstrate our proposed localization scheme's superiority in small robot scenarios, outperforming both the multi-tag approach and the EKF algorithm. In our experiments, E1 to E5 involved one robot with a rotating UWB tag and another with a fixed tag, while in E6 to E9. Both robots were equipped with rotating UWB tags. We analyzed the data in 3 ways. R1 utilizes onboard sensor data, R2 replaces UWB data with ground truth from Vicon for distance, and R3 uses Vicon data for velocity instead of wheel encoder data. Our findings summarized in table show an average error of around 0.3 meters. Notably, scenarios E1 and E6 exhibited significantly smaller errors, attributed to minimal wheel encoder error in stationary states. Furthermore, the smaller error in R3 across scenarios underscores the critical role of velocity measurement in localization accuracy, suggesting that employing high-precision odometers, like visual inertial odometry, can enhance overall system estimation.